Good morning, one and all. Myself, Vaidehi, working as Assistant Professor in Sri Muthukumaran Institute of Technology in EC Department. Today, the video lecture is from the subject Electromagnetic Fields for the 4th semester ECE student. Today, the lecture is from the Unit 1. Let's see about the introduction of EMF. In this course, we begin with an introduction to electromagnetic fields, which deals with the study of electric and magnetic phenomena and their interaction. Electromagnetic field theory forms the backbone of electrical, electronics, and communication engineering. Electromagnetic field theory explains how electric charges produce electric fields and how moving charges generate magnetic fields. These fields not independent but are closely related to each other. The behavior of electromagnetic field is governed by Maxwell's equations. Understanding EMF is very essential to analyze real-time engineering systems such as antennas, transmission lines, motors, and wireless communications. This unit lays the foundation for advanced topics like wave propagation and microwave engineering. Hence, a clear understanding of basic EMF concept is very essential. Let's see about the electromagnetic model. The electromagnetic model describes the relationship between electric fields, magnetic fields, charges, and currents. It provides a mathematical framework to analyze electromagnetic phenomena. This model is based on Maxwell's equations, which unify electricity and magnetism into a single theory. According to this model, electric charges create electric fields while moving charges produce magnetic fields. Time varying electric fields can generate magnetic fields and vice versa. This mutual interaction explains electromagnetic wave propagation. The electromagnetic model is widely used to solve field problems in free space and material media. It helps engineers to predict system behavior accurately. Hence, it is a fundamental tool in electromagnetic field analysis. Next, we see about the Maxwell's equations. Maxwell's equations are four fundamental laws that describe all electromagnetic phenomena. Gauss' law for electricity states that electric flux is proportional to the charge enclosed, that is, del F is equal to rho by epsilon naught. Gauss' law for magnetism indicates that magnetic monopoles do not exist, that is, del B is equal to 0. Gauss' law for the Faraday's law explains electromagnetic induction, where a changing magnetic field produces an electric field. Del cross E is equal to minus dou B by dou T. The Ampere's Maxwell law states that magnetic fields are produced by electric charge and time varying electric fields. Together, these equations link electric and magnetic fields are produced by electric current, and the Maxwell's equation form the theoretical base for electromagnetic waves. Hence, they are extremely important in EMF theory. Next, we see about the applications of electromagnetic model. The electromagnetic model has wide applications in modern engineering systems. It plays a crucial role in wireless communication systems such as mobile phones and satellites. Transformers and electric motors operate based on electromagnetic principles. Antennas and microwave systems rely on electromagnetic wave propagation. Sensors use EMF concepts to detect physical parameters. Field analysis helps in designing high frequency circuits and transmission lines. Medical equipments like MRI also uses electromagnetic theory. Power generation and transmission depend on EMF principles. Thus, electromagnetic models are essential for both power and communication engineering applications. Next, we see about the units and constants used in electromagnetic field model. Electromagnetic field analysis uses the SI system of units for consistency and accuracy. The fundamental units include meter for length, second for time, and ampere for current. Important electromagnetic constants include permittivity of free space epsilon naught and permeability of free space nu naught. These constants define how electric and magnetic fields behave in free space. The speed of light is derived from epsilon naught and nu naught. The electronic charge E represents the smallest unit of electric charge. These constants are universal and play a vital role in EMF equations. Proper understanding of units avoids calculation errors. Hence, units and constants are very important in EMF studies. Next, we see about the derived units in EMF. In electromagnetic theory, many physical quantities use derived units. Electric field intensity is measured in volts per meter. Magnetic flux is measured in Weber. Magnetic flux density is measured in Tesla. Power is measured in watts. These derived units are obtained from fundamental SI units. They help in representing electromagnetic quantities clearly. Correct usage of derived units is essential in problem solving. Misinterpretation of units can lead to wrong results. Therefore, engineers must be familiar with all EMF related units. These units are commonly used in both theory and applications. Next, we see about the vector algebra basics. Electromagnetic quantities such as electric field and magnetic field are vector quantities. Vector algebra helps represent both magnitude and direction. Vector addition and subtraction are used to combine multiple field components. The dot product is used to find the angle between vectors and work done. The cross product helps determine perpendicular vectors and rotational effects. Vector algebra simplifies complex field problems. It is widely used in EMF derivations. Understanding vector operations is essential before learning vector calculus. Hence, vector algebra forms the base for EMF analysis. Next, we see about the vector calculus. Vector calculus is an advanced mathematical tool used in electromagnetic field theory. The gradient represents the rate of change of a scalar field. Divergence indicates the source or sink strength of a vector field. Curl measures the rotational nature of a field. Laplacian is used in solving field equations. The operators are represented using the del operator. Maxwell's equations are expressed using vector calculus. Hence, vector calculus plays a crucial role in EMF theory. It plays in analyzing both static and dynamic fields. The equations are gradient del V, divergence del dot A, curl represented in del cross A, Laplacian represented in del square V. Hence, the proper understanding is necessary for solving EMF equations. Next, we see about the coordinate systems. The coordinate systems are used to describe electromagnetic fields in space. Different coordinate systems simplify field analysis depending on geometry. Rectangular coordinates are suitable for Cartesian structures. Cylindrical coordinates are used for circular or symmetric problems. Spherical coordinates are useful for radial field problems. Choosing the correct coordinate system reduces mathematical complexity. Hence, system has its own unit vectors. Coordinate transformation helps convert between systems. Understanding coordinate system is essential in EMF problem solving. They are widely used in antenna and field analysis. Next we see one by one about the coordinate system. First we are going to see about the rectangular coordinates. The rectangular coordinate system uses x, y and z axes. Unit vectors I, j and k vector represent directions along these axes. Differential length and volume elements are defined using dx, dy and dz. This system is simple and easy to visualize. It is commonly used in basic field problems. Rectangular coordinates are suitable for uniform fields. Many EMF equations are first derived in this system, then it is useful in transmission line analysis. Hence, rectangular coordinates are fundamental in EMF theory. The second coordinate system is the cylindrical coordinate system. The cylindrical coordinate system is defined using r, pi and z parameters. Unit vectors include AR, A pi and AZ. This system is useful for problems with circular symmetry. It is commonly used in coaxial cables and waveguides. Relationship exists between rectangular and cylindrical coordinates. Differential length elements change accordingly. Cylindrical coordinates simplify mathematical expressions. They reduce complexity in rotational field problems. Hence, the system is very useful in EMF applications. Next, we see about the spherical coordinates. The spherical coordinates uses r, theta and pi variables. Unit vectors are AR, A theta and A pi vectors. This system is ideal for problems with radial symmetry. Antenna radiation and point charge fields are analyzed using spherical coordinates. Relationships connect spherical and rectangular coordinates. Differential length elements depend on angles and radius. Spherical coordinates simplify field expressions. They are widely used in wave propagation studies. Hence, understanding this system is important in EMF analysis. Finally, we came to the conclusion of the topics. In this unit, we studied the fundamentals of electromagnetic field theory and we discussed about the electromagnetic models, Maxwell's equations and their applications. Units and constants and vector mathematics were introduced. Vector algebra and calculus form the mathematical foundation of EMF. Coordinate systems help represent fields in different geometries. These concepts are essential for advanced EMF topics. A strong foundation in Unit 1 helps understand wave propagation and field behavior. This knowledge is applied in communication and power systems. Thus, EMF theory is core subject in ECE. Hope you all understand. Thank you.